Good morning. In the next few minutes, I will show you how analytical hierarchy process and multi-criteria decision analysis can be used as a methodological approach that enhances decision making by systematically evaluating multiple criteria in the end-of-life textile management. I would like to show you the structure of this presentation. In more detail, I will start with a brief introduction, pointing out the reasons of this research and talking about the aim of the study. Then I'll show you the applied methodology, and finally we'll see the results section opening the road to the conclusions. The textile industry is fundamental since it provides significant contributions in terms of trade, employment, investment and revenue. However, one of the key challenges facing this sector is the fragmented and low-tech nature of supply chain operations. This often results in inefficiencies and missed opportunities for optimization. Recognizing the environmental impact and the potential for improvement, the European Commission has classified textiles as a priority product category for the circular economy, stimulating efforts to develop technological solutions for improving textile waste management, reuse and recycling. By addressing these challenges, the industry can move toward a more sustainable and efficient future. Fast fashion, as we know, revolves around the constant production of new styles at extremely low prices. However, this business model has a significant environmental cost. To face its negative impact, the European Union is focusing on reducing textile waste and prolonging the life cycle of garments through recycling initiatives. This effort is part of the broader goal to transition to a circular economy by 2050. The environmental challenges we face today, such as climate change and the depletion of finite natural resources, demand a shift away from the traditional take, make, dispose model. In this perspective, the European Commission in March 2022 proposed a package of measures aimed to accelerate the transition to a circular economy, as outlined in the Circular Economy Action Plan. Key among this proposal is the expansion of eco-design rules to make products more sustainable and recyclable. By moving toward a carbon neutral and fully circular economy, Europe can significantly reduce the environmental footprint of the textile industry. Taking into account the impact of textile industry, we can say that producing textile requires a vast amount of water, in addition to the land needed to grow cotton and other fibers. In 2020, the textile sector ranked as the third largest contributor to water pollution and land use. That year, on average, it took around 9 cubic meters of water and 400 square meters of land and 390 kilograms of raw materials to supply clothes and shoes for each European citizen. This data highlights the significant environmental impact of textile production, including both the resources used and the waste generated through the process. This image illustrates the material flow of the textile industry, particularly highlighting the production, usage, recycling, and disposal of textiles. The textile industry is largely dependent on virgin materials, especially plastic-based fibers. Recycling in the industry is minimal, with most materials either downcycled or sent to landfills and incineration. There are significant losses during both production and the uses phase, and the environmental impact extends to ocean pollution through microfiber leakage. This flow diagram highlights the need for more sustainable practices in textile production, use, and recycling to reduce waste and environmental harm. In this context, providing transparent information about the sustainability of end-of-life materials through their life cycle is crucial. Stakeholders across the supply chain, from manufacturers and retailers to consumers, require clear metrics and standards to make informed decisions to promote environmentally responsible practices. This work specifically explores the management of end-of-life textile, emphasizing the need for comprehensive data and guidelines to ensure all parties can contribute to more sustainable outcomes. The applied approach based on analytic hierarchy process and multi-criteria decision analysis offer a structured approach to decision making by systematically evaluating multiple criteria. These methods integrate expert insight and stakeholder perspectives, ensuring that end-of-life strategies are not only technically feasible, but also socially acceptable and economically viable. The inclusion of experts from diverse fields enhances the decision-making process, providing specialized knowledge and innovative solutions to tackle the complexity of textile recycling. Their contributions are essential for developing robust frameworks that optimize resources use, reduce waste, and mitigate potential socioeconomic impacts associated with the adoption of new technologies and business models. This work involves the comparison of four alternatives defined as following: A1 reuse, A2 mechanical recycling, A3 chemical recycling, A4 landfill. This is these alternatives are evaluated according to 10 criteria that are selected to assess the different dimensions of sustainability: social, economic, technological, and cross-cutting dimensions. 20 experts were selected, comprising 5 from academia, 5 from industrial sector, 5 consultants, and 5 from the policy domain. They were asked to compare each criterion against to the others in an iterative process using the analytic hierarchy process. As a result, each expert provided a ranking of the 10 criteria. After that, we asked the expert to give a score from 1 to 10 to the 4 available alternatives for each criterion. At the end of the analytical hierarchy process, we note as the criterion sustainable policy was considered the most relevant for academics, industrials, and politicians. Meanwhile, consultants consider an economic criterion, the value added, the most significant. Academics consider the technology efficiency as the less important to consider in sustainable practices, while human rights conditions are the less relevant for consultants and industrials. For the industrials, also job opportunity criterion is the less significant. According to the politicians, the technological improvement is the less significant. After the criteria ranking was established, we asked to the 20 experts to assign values to each alternative. The table below presents the average values obtained. Among the alternatives, A4 was deemed the least sustainable option across all criteria. In contrast, A1 reuse was identified as the most suitable alternative when considering environmental, social, economic, and transversal aspects. Meanwhile, A2 mechanical recycling emerged as the best option in terms of technological consideration. The set table was then built by multiplying each values of the alternatives by the weights associated with the defined criteria. It can be seen that whether applying the weights defined by the expert for the criteria or using an equal weight for each criterion, the alternative considered as most suitable is always reuse, followed by mechanical recycling and then chemical recycling. The alternative deemed least sustainable is always landfill. In conclusion, the analytical hierarchy process, combined with multi-criteria decision analysis, provides a systematic methodology for enhancing decision-making by evaluating multiple criteria. The analysis identifies A1 as the most sustainable alternative, followed by recycling, A2 and A3, regardless of whether the hierarchy process laws are applied. A4 is deemed the least sustainable option, landfill. Incorporating insight from experts and stakeholders ensure that end-of-life strategies are technically feasible, socially acceptable, and economically viable. Their contribution of the experts are vital for developing effective frameworks that optimize resources use, reduce waste, and address potential socio-economic impacts linked to new technologies and business models. Thank you for your attention, and it's all. That's all.